Good day, esteemed panelists and advisors. I am Emerson Dela Cruz Cumlat Jr., an MEP student. Today, I am presenting my practicum proposal as part of the requirements for the Masters of Engineering in Electronics Engineering degree at Mapúa University. I am a telecommunications professional working overseas as a fiber network designer in Fiji, a South Pacific country, for over 7 years. The title of my practicum research is Smart Optimization of Fiber Optic Network Design using the Prim-Dijkstra algorithm. My research is directly related to my job, as I understand the critical role fiber optic communications play in the telecom industry and our daily lives. I identified the problem in this field and explored a solution to address it, which led me to develop this practicum study. This presentation is structured into three chapters. The following follows the paper write-up. Chapter 1 for the introduction, Chapter 2 for the review of related literature, and Chapter 3 for the methodology. Let's proceed on the first chapter. Fiber optic technology offers numerous benefits including high bandwidth, reliability, and security. Key factors for modern applications like cloud computing, Internet of Things, and HD media streaming. The increasing growth of digital services and cloud-based applications has considerably raised the demand for fast and dependable internet access. Fiber optic technology, with its higher capacity, reduced latency, and increased security, has emerged as the ideal medium for the next generation networks. Conventional copper-based networks, once adequate, now face challenges in supporting emerging technologies. The shift from copper infrastructure to fiber optic networks is driven by the demand for higher bandwidth, reduced latency, and enhanced reliability. Despite its advantages, fiber optic deployment faces significant challenges, including high installation costs, complex infrastructure requirements, geographical constraints. Additionally, ensuring network efficiency while overcoming geographical, environmental, and regulatory constraints presents major challenges in achieving optimal performance and scalability. However, traditional network design methods often results in high costs and inefficiencies, necessitating the development of smart optimization strategies. In my current work, I use AutoCAD as a design software tool and Microsoft Excel for bill of materials calculations, similar to the software used by other engineers in on their projects. However, these tools rely solely on the designer's input and do not provide feedback on whether the fiber network design is efficient or optimized. Manual planning involves human-driven decision-making, where planners rely on their knowledge, experience, and intuition to create plans without the use of automated tools. Heuristic-based planning utilizes predefined rules or strategies to efficiently generate solutions by focusing on likely successful outcomes based on past experiences or simplified models. As fiber designers, this is the standard practice we follow, and we don't depend any automation tools. The need for cost-effective, optimized solution in fiber optic network design arises from the necessity to minimize infrastructure cost while maximizing performance. Smart optimization method help achieve this by utilizing advanced algorithms to reduce network deployment costs, improve resource utilization, and ensure scalability for future growth. During my research, I discovered two advanced algorithms, Prims and Dijkstra, that have yet to be applied to enhance fiber optic network design. This prompted me to explore these machine algorithms to achieve my goal of optimizing fiber network designs. Moreover, this, this study aligns with the United Nations Sustainable Development Goals, particularly SDG 9, the Industry, Innovation, and Infrastructure, and SDG 11, Sustainable Cities and Communities. Enhanced fiber network deployment supports digital inclusion, economic growth, and the sustainable expansion of urban and rural infrastructure. This study focuses on optimizing fiber network design in urban and semi-urban environments, as urban areas have dense node distributions while rural areas tend to have scattered nodes. Since rural fiber networks often follow straightforward paths, they offer limited opportunities for optimization. Therefore, the research will concentrate on a case study involving a complex fiber network where the algorithms will be applied to improve the design. The scope is limited to the optimization of existing fiber optic infrastructure and their enhancement through machine algorithm solutions. We move to the second chapter of this practicum research, which is the review of related literature. Implementing a fiber network design begins with planning and design, which includes site surveys, selecting the appropriate topology, and securing necessary permits. The next phase involves deployment and installation, where the fiber cables are laid either underground or aerially, followed by splicing, termination, and thorough testing using OTDR and signal loss measurements. Finally, the infrastructure is captured in an inventory, the network is activated and optimized, ensuring proper configuration, monitoring for performance, and conducting maintenance to sustain efficiency and reliability. This research focused on the planning and design stage of the implementation. Fiber network topology define the structural layout of fiber optic connections, influencing factors such as network reliability, scalability, and cost efficiency. Common topologies include point-to-point, star, ring, and mesh configurations, each offering unique advantages in terms of redundancy, cost, data flow, efficiency, and fault tolerance. Designing large-scale fiber networks requires careful consideration of factors such as network topology, scalability, and redundancy to ensure long-term efficiency and reliability. Designers must also account for geographical constraints, budget limitations, and regulatory requirements to optimize deployment while minimizing cost and maximizing performance. Let's explore some previous studies related to optimizing fiber optic network design. One notable approach is fiber indexing. This is introduced by the cable vendor CommScope. Here, we have a typical fiber distribution network for a hub serving up to 240 homes. In this setup, individual cables extend from the hub to each terminal, represented by the blue circles, in a star topology. With each terminal serving up to 8 homes, the initial cable length used in this configuration is 20,000 feet. With fiber indexing, the total cable usage is significantly reduced. This technique utilizes a linear daisy chain topology, which terminals serve multiple functions. As a result, the total cable length decreases to 5,500 feet. Another ongoing study focused on optimizing fiber network is the hybrid network design, which integrates passive optical networks, the PON, and active optical networks, the AON, to achieve a balance between performance, scalability, and cost effectiveness. In an active optical network, customer premise devices are connected in a point to point requiring more cables and power consumption. In contrast, passive optical networks, the PON, utilizes unpowered optical splitters to distribute signals from a central office to multiple endpoints, making them more cost efficient and energy saving, though bandwidth is shared among users. Fiber optic cable is one of the most expensive components in network deployment. Optimizing cable usage through efficient network design can significantly reduce overall project expenses. Existing research on fiber optic network design often focuses on either cost reduction or performance enhancement, but lacks a comprehensive approach that integrates both aspects effectively. This gap highlights the need for smart optimization techniques that balance cost efficiency with network performance, ensuring scalable and sustainable deployment solutions. We will then try to resolve the gap on this research using the proposed machine algorithms. Our research conceptual model begins with the input, which is the initial fiber network plan. This plan will be processed using Dijkstra and Prim's algorithms. The resulting output will be an optimized fiber network design, which we will then evaluate and compare. Prim's algorithm is a method for connecting all the points in a network with the least total cost. It begins by selecting any point as the starting point. Then it looks for the cheapest connection to a point that isn't already connected. The algorithm keeps adding the least expensive connections to the network until every point is connected. The result is a network where all points are linked together with the smallest total cost without forming any loops. Nodes in fiber optic networks serve as connecting points, such as switches or routers, whereas edges represent fiber optic cables with weights allocated based on length, cost, or delay. Prim's approaches is used to reduce the length by generating a minimal spanning tree that links all nodes with the smallest overall connection length. The flowchart typically involves selecting an initial node, marking it as a part of the tree, and then iteratively choosing the right edge with the smallest weight that connects the tree to a node outside it. From this flowchart, we can create a program out of it using C++. The other hand, Dijkstra algorithm is a method for finding the shortest path between 2 points in a network, like finding the quickest route on the map. It starts at the starting point and looks at all the possible paths, keeping the track of the shortest distance to one each. Then it picks the next closest point and continues exploring, updating the shortest distances as it goes. The algorithm keeps doing this until it reaches the destination point, always choosing the shortest path. In the end, you have the quickest route from start to finish, based on the least amount of travel or cost. The shortest path computation in fiber optic network is critical in establishing the most effective route for data to take, reducing delays, and enhancing network performance. This strategy assures that data transfer is both speedy and cost effective, adding to the network's overall efficiency and dependability. The flowchart starts with marking the source node with a tentative distance of 0 and all other nodes with infinity. Then iteratively selects the node with the smallest tentative distance, updates the distance to its neighbors, and mark it as visited. The process repeats until all nodes have been visited or the shortest path to all nodes is determined. From this flowchart, we can create a program out of it using C++. We then moved on our last chapter to discuss the methodology of this research. This scenario outlines the design and implementation of a cost-effective and efficient fiber optic network to connect 20 critical nodes of a telecom company in Manila City. These nodes represents a building, a customer, or a key connection points that require a high-speed internet connectivity. The main goal is to minimize the cost of laying the fiber optic cables while ensuring all nodes are interconnected and that data transmission paths are optimized. To achieve this, we utilize a combination of Prim's minimum spanning tree and Dijkstra shortest path algorithm. This is the visualization of a graph representing a region with 20 nodes. The total length of the vertices, which represents fiber cable length, is 257 meters. We need to represent the distance between nodes in a matrix format. This will later be used on our program. For example, the distance between node 0 and node 9 is 19, and units for which is reflected in the cell at row 0 and column 9. A 0 in other cells indicates that there is no direct connection between the corresponding nodes, such as between node 1 and node 2. This is the C++ script of and program for Prim's algorithm. The output will specify which nodes should be connected and the corresponding edge lengths in the graph. Prim's algorithm is applied to the constructed graph to determine the minimum spanning tree. This algorithm identifies the subset of edges that connect all nodes with the minimum total weight, ensuring a total cost-effective network. The total vertices length after running the Prim's algorithm program is 116 units from 257 units before. So this is the C++ script and program for Dijkstra algorithm. The output will specify which node should be connected and the corresponding edge lengths in the graph. The distances from the source node N0 to all other nodes are initially set to infinity, except for the node itself, which is set to 0. Then the algorithm iteratively selects the node with the shortest known distance, updates the distance to its neighboring nodes, and marks it as visited. This process continues until all nodes have been processed. Finally, the total cost of the fiber optic installation for the shortest path is determined by summing the weights of the selected edges, which is 147 units on this case. So this is how we calculate the fiber optic network cost. For this scenario, we assume a cost of 650 pesos per meter for laying the fiber optic cable. On heuristic approach, we come up with this cost 167,000 pesos in Prim's when we apply for Prim's algorithm from the heuristic approach design. The cost went down to 75,400, and when we applied the extra algorithm, the cost went down to 95,000. The summary of cost is tabulated on this table. By utilizing Prim's algorithm and Dijkstra's shortest path algorithm, we have designed a cost-effective and efficient fiber optic network for a hypothetical region with 20 nodes. This approach ensures that all nodes are interconnected with the minimum total cable length, greatly reducing installation cost while maintaining optimal data transmission paths. The scenario highlights the practical application of graph theory in addressing real-world network design challenges, offering a strong foundation for future research and implementation in larger, more complex regions. Overall, While manual and heuristic-based planning remains relevant for smaller or resource-limited projects, algorithm-based approaches provide superior efficiency, cost saving, and scalability. The integration of algorithm-driven methods are a preferred choice for large-scale and complex fiber deployments. This study underscores the significance of graph theory in solving real-world infrastructure challenges and lays a foundation for future research and implementation in more complex and larger-scale network scenarios. The methodologies and results presented here can serve as a valuable reference for engineers and researchers working on the design and optimization of fiber optic and other types of networks. Thank you for listening, and God bless.